your endurance? Where's your perseverance? Where's your tough going when the going gets tough? Oh, that explains it. Okay, so somebody said a -2. We're going to use that. You guys have gotten there pretty quickly, right? When we tried 2 and -2 next? Whoever told me -2, like you actually got it, right? Alright. We're throwing the -2 in. Hopefully whoever gave us that. They're actually helping, not just making us keep going. Positive one didn't work, right? Huh?
No.
Well,
3 works.
Look, it's amazing. Nicely done. Nicely done. Now we had a 4th degree. Now what do we have? A 3rd degree, because we took away 1, right? We took away a degree by dividing by. -2 was in the box, but guys, what factor is this talking about? Say it loud, David.
X plus 2.
Plus 2. X plus 2, right? So we just divided our whole polynomial by x plus 2. That's one factor. X plus 2 has a solution of -2. Now what do we do?
You can group that bad boy. Group them.
Okay. You can try grouping. If you want to try grouping, you could start by writing the 3rd degree, then the squared, then the single, and then a plus. Wait, really? You can pull out a 9x squared, and so you just get an x minus 3. You can pull out a -4 and get an x minus 3. Spoiled, right? Let's say you couldn't group. I know. We can and we will. But let's say we couldn't group, because sometimes you can't, to be frank. What would you do? You could go back to these and say, all right, let's pick up where I left off. +3, -3, +4, -4, and keep going. You could look at this and you could say, wait a minute, it's no longer 24 and 9. Who is it now? 12 and 9. And you could possibly say, hey, let's reevaluate for him and see if I can narrow down the options at all. Like, for 12, I have 1 and 2 and 3 and 4 and 6 and, well, 8's not there. 24 is not there. Do we still kind of have a lot, though? But we could pick up from here and have a bit fewer options. And we already tried 1 and -1, so forget that. I'm assuming those of you guys that got to -2 tried +2 first. I would have. I don't know if you did. Oh, well, but you might start going with 3, -3, 4, -4, 6, -6, 12, -12. We don't usually get to the fractions unless we're desperate. Right? Honestly. But, what did you notice? What did you notice about what we're doing? It's hard, but we just noticed what? Do we have to go through that process and try to find another one that works? No. What can we do? Group. So pull out that 9x squared. I just wanted to let you know if it didn't work, how to keep going. But since you can group in the sense of pull out some common stuff for the first 2 terms, like 9x squared, and get x minus 3. Pull out a, what would you pull out again? -4, and get a, right? Because you pulled out a negative, so x minus 3, that's pretty important. Then we end up with x minus 3 times 9x squared minus 4. Does it technically matter what order you write those factors in? No, because there's this commutative property of multiplication, right? A times b is the same thing as b times a. So, we're okay. But how do we keep going? Can we keep going? Simplify. By factoring some more. And who can we factor some more? Not the x minus 3. Wait. We're keeping did we leave out way up here?
That bad guy.
So don't forget that when we're talking about f of x, we already took away an x plus 2, so he's one of our factors we need to keep on going in the answer. Now we didn't really need to write him here because he wasn't actually in this answer, right? He was up here in the synthetic division. But when we're writing a whole function, we better keep that x plus 2. X plus 2 is fine. X minus 3, he's golden. 9x squared minus 4, I can go one more step and say, who is the square root of 9x squared? Who's the square root of 4? This is a difference of squares. Right? Oh my goodness. So what would now? They're not asking for this next question. So box it. You're done. But if they asked, what are the zeros, just so you can compare with our possible zeros and make sure they're all in the list, and I think homework has you do that a couple times. What are the zeros, and are they all included in the original possible list? My zeros are x equals. Oh, sorry, I was starting left to right. -2, 3, plus or minus. Were they all there? Yeah. And to be honest, if you look at it, the 1s didn't work, but a 2 worked, a 3 worked, so we would have been able to break it down pretty quickly, even if they hadn't been able to. Questions, Austin?
There's 4 zeros because the degree is 4, right?
Yes.
Yes.
Yes. But remember, those 4 zeros don't all have to every time be real. Sometimes they can be imaginary. All right. Guys, let's get back in our notes. I had us walk through this example because this is the big idea. This is the main idea of what you're able to do in section 2.5. Now, homework exercises, the section digs a little deeper. In the sense of it doesn't stop here and say, okay, that's good, that's all, let's move on. It does have you dig a little deeper in a few different ideas, all applying to this whole idea of polynomials having the same number of zeros as their degree. Some are real, some are imaginary, etc., etc., etc. So we're going to work through some of those today. There are 2 kind of big theorem, rules, properties, characteristics at the end that we're going to talk about. But it's a very, very small part of homework because I just want you to see the idea. I don't need you guys to memorize them. I'm not going to test you on them on a quiz or a test. So you're going to see a couple theorem-ish sort of things, a couple rules. They're kind of long, they're kind of tedious, but they're actually quite helpful when, look, you have a polynomial with a stinking load of possible zeros that you need to go looking through and testing. So when you have all kinds of possible zeros, the rules that we're going to look at the very end of today help you say, hey, start plugging in. Oh, you went too far. Stop. Forget all the rest that are higher or forget all the rest that are lower. And that's kind of useful to narrow down a huge list that we have to work with. So we'll come back to this example just a little bit later. But for right now, let's get back in the section. We're going to do some homework help today. I think I skipped a page. Where is he? Did I skip a page? No, I didn't. Okay. We're going to do some homework help today, and we're going to do just a couple rules at the end to help us out. So think of today basically as a big homework help, but also as a digging deeper day in the sense of we've seen the big idea of 2.5. Nasty polynomials, what are their zeros, what are their factors? Let's go just a little bit more in depth and see if we really understand what's going on. So, I said a little while ago, a 4th degree polynomial, yes, it will always have 4 zeros, but all 4 do not need to be real. Some of them could be imaginary. And any zero with an imaginary component is called a complex zero. It could just be imaginary, like 2i or 3i, or even just plus or minus I. It could just be imaginary, or it could be real and imaginary. But remember, all of that falls under the umbrella of complex, right? And a big clue for us to remember. For complex zeros. Basically, in order for complex zeros to come out of a polynomial with only real coefficients, like if you were to look at it, you don't see any imaginary numbers to begin with. The complex zeros must always come in pairs. And not just any pairs, but conjugate pairs. And what I mean by that is the signs are different of the imaginary pieces. So if I have an a plus bi, I must have an a minus bi. If I have a positive bi, I must have a negative bi. So if a problem says, hey, guess what? It has a complex zero, you're like, it has two. Does that kind of make sense? If it has one, it has to have both. Because you can kind of think about it, and we'll see an example of it. When you multiply complex numbers together, you get I squareds, they turn into real numbers. That's kind of what's going on. So in order for complex zeros to come out of polynomials with only real coefficients, they have to come in pairs. So, if you were given the following example, which is so weird and so different than what we saw in our spiral, which was nasty, but at least we recognized it. This one, they say, hey, here are a few clues. Take it, run with it, and find me the polynomial it came out of. Aw, stink, we're working backwards. They're telling us clues, but we have no idea, well, we don't have the polynomial to work with. So, the degree of 4, all that means is, well, it has to go up to x to the 4. What else does that mean? How many complex zeros is it going to have? Some might be real, some might be imaginary. We have 4 complex zeros. Real coefficients. Okay, imaginary numbers aren't allowed to stay. Somehow they must simplify away. Wait, we just said 4 zeros and they only gave us... So what do we do? Since they gave us one 3i, there must be a negative 3i, so therefore we can say, you tried to trick me, but not today. There he is, 4. Now how can we take zeros? Think. If zeros are like the a's that we put into synthetic, how can we make factors out of those zeros thinking who was there before, hopefully on our way to getting the polynomial himself? Yeah, let's start putting parentheses. And how many parentheses am I going to have? Well, how many zeros do I have? Okay. So, the negative 1 must have come from... Sounds good to me. Think about it. X plus 1, what's the 0? Negative 1. Oh, the next 0. Hey, it has a multiplicity of 2. That's good to know. How much could the next 0?
Plug it in.
How? How do we plug in negative 1? Getting there. Nice job. Right now I was just thinking x minus 0. We did x minus negative 1 was x plus 1, x minus negative 1 plus 1, x minus 3i, and x minus negative 3i. Now some of you might be able to look at this plus or minus 3i thing and be like, hey, I'm pretty sure that came from plus or minus square root of negative 9, and would you be right? Yeah. So you might be able to jump to where I'm about to go a little bit faster than me. And I think it was Caleb or someone. I heard someone say x squared plus 9. Perfect. That's exactly where we're going. But how do we get there? Well, is this a polynomial? Yeah. It's nice and factored. Quick question. Are all the coefficients real? You got 3 i's in there. And I don't really see the 4th degree. I see 4 factors. They want me to get back to the very original problem. How do I do that? How do I undo factoring? There's 4 of them. Well, take them 2 at a time, yeah? Let's take the first one. And we get x squared plus 2x plus 1. You guys kind of okay with FOILing? You multiply x plus 1 times x plus 1. There we go. Not killing puppies today. Hopefully not any day. When we go to the next one, a little bit harder, but let's see what happens. Let's see what happens. When I have first, that'll just be an x squared, yeah? When I have outer, who's that? 3ix, ew, that's true. Inner, negative 3ix. 3ix minus 3ix, 0. It's a difference of squares. And then multiply the last, and what do you get? Yeah, minus 9i squared. But hold on. Forgot my squared. What can we do with an I squared? Make it a negative 1, and negative 9 minus negative 1 is going to end up being positive 1 times 9 plus 9. Do you guys see where the plus or minus square root of negative 9 comes from? Minus the 9 plus or minus square root both sides. Oh. Are we close? Oh, we're stinking close. We have only real numbers in our polynomials. That's a good sign. It's kind of factored, but kind of not, because we could have gone further. We came from a further factored form. So how do we technically finish this off and see what the original problem would have been? Bigger form. Yeah, distribute everybody to everybody, right? Polynomial multiplication, remember, it's like the other form. You take one term at a time, and he has to go to both the others. So I end up with x to the 4th plus 9x squared. Go to the next term. He has to go to both of the others. Plus 2x cubed plus 18x. And we have one last term, and he has to go to both of the others as well. Distribution doesn't change, just how it looks changes a bit as our pieces get bigger. All we gotta do is combine right terms. And booyah, we got ourselves our polynomial. X to the 4th. So I only have 2x cubed, right?
Yep.
But I have a 9x squared and a 1x squared. You guys get 10x squared? Sweet. I have an 18x. And I have a 9. I think he might have even been easier than the one we did in the back of our spiral.
Yeah.
But he was different. He was weird from the get-go, right? We had to think backwards. But maybe it wasn't as impossible as it seemed. But what was the key? Knowing that this one meant that one, right? Knowing they came in pairs, and knowing how to go from zeros to factors. That's about it. Otherwise, we were just distributing, we were multiplying, we were getting our polynomial after plugging in I squared is negative 1. All right, so if one of these comes up in homework, you'll know how to attack it? Okay. So what if hold on. Let me actually put one more homework help before this page. That page is like a big, huge sum up of the entire section. Yeah. Let's go this one next. Whew. What if we were given this one?
Do it.
Why is kind of? Except with the 3i, it's going to get really messy really fast. Good idea. Good idea. But not perfect. Synthetic, remember, it's best if we just have a single constant. Here's the problem. Does anybody catch the typo? I'm fixing it right now. It's not a factor because there's not an x. What is it? A 0. Or we could call it a solution. Solution. What? Solution. Now, what's one way we could attack this problem by ignoring completely the clue that it gave us at the beginning? We could plug it in, but hold on. I don't think some of you realize what you're saying when you say plug it in. When you say plug it in, you're saying put 1 plus 3i in and have to raise it to the 4th power.
Yeah. Simplify.
Wait, guys, does it really matter? Don't we know what it's going to equal? Because the remainder is 0 because it goes in.
Let's test it.
So, you go testing that on your own time. Let's come back. Let's not do that. Although, thank you for the idea. What's something else we can do? That doesn't help us. That just tells us what it already tells us. We can do the plus or minus thing. I'm going to come back to you, Austin, but I heard the plus or minus thing, which means if this one is a 0, who else has to be a 0?
Negative.
1 minus 3.
Just the imaginary part
Oh.
is not the real part.
True.
A plus bi, a minus bi. Remember, we wrote that down a second ago. The 1 stays the same. Great, so we know 2 zeros. Wait, how many zeros are there total? 4. So we know half of them. But how do we get the other 2? Can't do synthetic. Plugging in, we'll just get a 0, which we already know. Why can't we do synthetic? Because it's nasty with imaginary numbers. How can we make the imaginary numbers become real? Kind of squared. Multiply what though?
3i.
Negative squared root of negative 1.
Oh my, you're dying. 3i squared.
We could put in a negative square root of negative 1. It kind of could. What would we get when we multiply them together?
Factor of
I think it'll make most sense. It's just gonna be a little messy if we go to the factors. Kind of like we did in the last problem. Except it's a little bit harder because there's a 1 minus 3i, 1 plus 3i, and not just a plus or minus 3i. But technically, our factoring, or how we make factors, remains the same. Because we take the 0 and we do x minus wherever the 0 is. And the problem before was just a 3i, so it was just a 3i there, but this time it's that whole piece. And then we have the other one, and we have x plus, nope, it's a minus again. X minus who? X minus the 0, 1 plus 3i. We're building our polynomial, we're just missing somebody, right? That only gets us an x squared. Now how do we make it all nice and pretty and all nice and real? Some people were saying multiply, and I totally agree, but let me show you why. When we go to multiply these two together and figure out who this is so that we can actually divide him away, oh, that's the way to go. We're going to do first, that's x squared. We're going to do outer and we're going to do inner, which isn't pretty. Him times x with a negative in front. Him times x with a negative in front. It's not pretty, but it's possible. We can do some distributing. We can do some simplifying. But we also will have the 1 minus 3i times 1 plus 3i. So those of you guys that were saying, hey, let's multiply, you're actually right, because we are going to have to multiply to figure out who on earth is this thing and where on earth did it come from. Ricky.
Can't you multiply 1 minus 3i and 1 plus 3i just by itself, and then use long division, and then you can get another factor out of it?
But when you multiply 1 plus 3i and 1 minus 3i, which we're going to do in a second, you are going to get a constant, but you're not going to know the polynomial necessarily that that constant came out of.
Okay.
Long division, you can't just use the number, you need to use the whole expression. Does that make sense?
Yeah.
That's the dilemma. So then we go ahead and get back here. So that's why I'm saying multiplying, perfect. We have to multiply, but we need to see who this entire our thing really is. So I'm just going to go through and simplify as much as I can. Because right now, this is gross. But maybe, just maybe, don't forget to distribute the negative. I'm going to simplify. Things will get just a little bit better. I went one, I distributed and went the other, I distributed and went the other. All I have left is this little guy. And this little guy, I'm going to have my first, my outer, my inner, and my last. Whew. Does anybody see anything I can get rid of? Who else? Well, that's nice. All my imaginary pieces are going, oh, he's still there. Wait. It's a square. So who is I squared? It's -1. So I can make this -9 times -1 instead, which is going to be a +9. Got this. I have my x squared. Awesome. I have, repeat, this is what I meant. I have a -2x. I wouldn't have known that otherwise. And then I have a +1 and a +9. That's a plus. I've just broken my little polynomial down into where my nasty 1 plus 3i and where 1 minus 3i came from. How can I figure out the other part if I know this? Synthetic? No. But what can divide? Well, good idea. But if I factor him, guess where he goes? Right back there. How do I use knowing that this polynomial goes into this polynomial?
Long division.
Long division. Because if I'm trying to find my question mark, if I'm trying to find him, and if I know f of x, can't I just say f of x divided by x squared minus 2x plus 10 equals the rest of the square? Probably a little bit beyond you. But either way. It was an old radio program. And now you know the rest of the story. Anyway. Put in our big ol' f of x. Say, hey, I know that this is going to divide in and it's going to give me the rest of who you are. And the rest of your zeros. Without having to go through and test 60, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 5, plus or minus 6, plus or minus There's a lot in 60, even more than 24. So, we'll just do one division and I know for sure it'll be almost done, yeah? So let's divide it by that nasty x squared minus 2x plus 10, and yet we know that's going to work. And we know our remainder is going to be 0. After all that craziness, this is what we're down to. X squared, yeah? Your x to the 4th minus 2x cubed, don't kill anything, plus 10x squared. It's division, so we subtract. But we remember, subtract everything, yeah? Oops, that was a plus. That cancels. We have negative x cubed minus 4x squared. You guys double checking my math? Bring down that 2x. Now I'm going to bring down the minus 62. You never know when you're going to use them. We'll just keep them stringing along. Now we have a negative x, right? That'll get me my negative x cubed. A positive 2x squared minus 10x. Don't forget, we subtract everything. So we're going to have to, just like we did up here, we're going to have to distribute that negative to everybody. That goes away. We end up with negative 6x squared, yeah? Plus 12x minus 60. negative 6x squared plus 12x minus 60. Oh my goodness, this is awful unless you notice, wait a minute, I already know the end. If I did it right. What does that mean? Whew! Who's my question mark? X squared minus x minus 6. So therefore I can say, I want to find all the zeros.
X minus 3.
F of x is equal to the nasty x squared minus 2x plus 10 times x squared minus x minus 6. Can you guys do that factoring real quick? X minus 3. X plus 2. So my zeros are, oh, they already gave me the first ones. 1 minus 3i, 1 plus 3i. Remember, they came from that first piece. So we're not even going to touch that first piece. We already know who he comes down to be in sense of the zeros. Then we have a positive 3 and a negative 2. There are all 4. Dun, dun, dun.
That was too long.
But you made it. Like this one? Oh, maybe one. Oh, come on. Alright, I told you guys we were going to do lots of homework help, right? Which is pretty much what we've been doing, well, practically the whole time. But I also said at the very end, we were going to talk about 2 quick tests, 2 quick clues. Now, before we get to those 2 quick tests, those 2 quick clues, pause, pause, pause. What is this page? You have a polynomial, you need to factor, what am I telling you? It's a summary of, yeah, the whole thing, right? You need to figure out your possible zeros. You can try synthetic, you can try plugging in, you need to find ones that work. Other tools is what we're about to talk about. And then you can always, in homework, it allows you a couple places to use your calculator to kind of narrow down whenever you have tons and tons of possible zeros. I'm going to go ahead and put this slide, guys, because it's like a summary of our whole section. I'm going to put it right before the homework. And if you want to write it down, it's a great thing to put into your notes as in, when you need to factor a polynomial bigger than a quadratic, think this page, okay? But remember, I said there were 2 little tricks, 2 little clues that are nifty, especially when you have stuff like, remember the 24 and the 9? Oh, that was brutal. And if we'd actually had to keep testing, because the first numbers wouldn't have worked out, these 2 clues help us kind of know when to stop testing or kind of narrowing it down as to what numbers are possible. Now I do want you to write it down. You don't need to memorize it for a quiz. You don't need to memorize this for a test. I'm just showing you how it works and how it can be kind of nifty. I just want to show you how it works and how it can be kind of nifty. So if you're like, I don't need to memorize it, I'm not going to write it down. Okay, well, that's fine. I'm going to show you how it works. Just because it is kind of spooky. Descartes' rule of science. Snazzy guy, Descartes. He's a philosopher, he's a mathematician. He was the one that figured out the whole XY axis thing as a nice way of showing something's position with a horizontal vertical. Smart guy. This one helps us narrow down to some degree how many positive real zeros and how many negative real zeros. And if you think about that huge list of plus or minuses, it might be nice to know exactly how many we were looking for. It might be nice to know exactly how many we were looking for. And here's how the test goes. So you guys can be writing the test. I'm going to be using the test. Remember, you don't have to memorize it. And it's only literally like 1 or 2 problems in homework, just to see the idea. And once again, it's for something with tons and tons of nasty possible zeros. I'm using an easy one as an example, but like the plus 60 or the 24 and the 9, and we had so many to deal with, this narrows down the search. For positive real zeros, you want to look at the sign of, the changes in sign of f of positive x. And for the negative real zeros, you want to look at the sign or changes in sign of f of negative x. So positive, we're looking at the changes in sign of f of positive x. Negative, we're looking at the changes in sign of f of negative x. Changes in sign? Yeah. F of x, you just keep them and you ask, as you move left to right from one term to the other in descending order, how many changes in sign? None? Yeah, right? A positive to a positive to a positive. Nothing changed. So how many changes in sign were there? So how many positive zeros can there be? 0 or less than that by an even number. 0 or 0 minus 2 or 0 minus 2. Can you have negative 2 zeros? Like that many zeros? Doesn't make sense. So how many positive real zeros are there? Oh, look, no changes in sign, 0. What does that mean? All your list of possibles, which isn't a lot for this one, don't choose any of the positive ones. They're not going to work. Okay, that can cut down like half my work on a big problem. Does that make sense? The negative ones say, hey, plug in and find f of negative x. So plugging in a negative cubed, that keeps my expression, makes it negative. Plugging in a negative squared, that stays the same. All right, cool kids. How many changes in sign in this one? Just one. Well, if there's only one change in sign, then how many that's not possible. Sorry. Negative. How many negative real zeros can we have? Either, what's that mean? 1, or 1 minus 2, or 1 minus 4, or 1 minus 6. Those are all negatives. There's only one negative real zero, which means no positive real zeros, 1 negative real zero, 3 total, 2 imaginary. I already know exactly what I'm looking for. And I haven't done any plugging in right now. I just used his cool rule. That's one cool trick. Once again, I don't want you to memorize it. I'm not going to give you, if I was a college professor maybe, one nasty huge polynomial and say, here's your test, go. But if I did, this would be super helpful.
You should.
I should? Should I? No. So there's one more cool tool. And here's the last one. There's one more cool tool. Remember, you don't have to memorize it. Some of you might just be like, I'm not going to write it down. Fine, whatever. But the one more cool tool says you can actually figure out from synthetic division what number, when you're plugging in, says don't go any higher, there's nothing there. And what number would say, hey, don't go any lower, there's nothing there either. It's called the upper and lower bound rule. And basically it says, look at the answer in synthetic division when you plug in the number that you're looking at. So you're just doing synthetic, you're chilling, you're going along. An upper bound is always going to occur when you do synthetic. 192, right? And there's no change in signs. Guess what? Don't go any higher than 4 with the polynomial, which I know this one wouldn't be a possible 0, but that list is 60. Don't go any higher than 4. There's nothing up there. It says, hey, it's an upper bound. And you just have to say, hey, look, there's no change in signs. The rule says, yeah, don't go any higher. And then down here, what's going to happen if you plug in a negative 1 according to our cool nifty rule? What it says is, as you plug in, wait and pause if the bell rings, I'm right here. Yeah, no, I just don't like it. One more, 3. 3. -3, -2. Hold on, what went wrong?
I have no clue.
Something went wrong. Let's look at it tomorrow, but it's all today's time. Me either. Something went wrong. It alternates the lower bound. Bye guys, talk to you tomorrow.
Your work's right.
Yeah, right? Bye.
Why are you at this point?
It's supposed to go.
Let's go back, forth, yeah.
Orange. Orange marker.
I probably got it wrong.
Oh.
I served with it's very,
It looks like they do.
it does look like a game.
Aw, buddy. Get it after school. I'll work on it.
Okay, thank you.
Next time, go capital letters or something.
Yeah, that's what my mom said when I was talking to her.